Myself, Mrs. Afroz Patan. I am working as Assistant Professor in Department of Pharmaceutical Chemistry and Analysis, School of Pharmaceutical Sciences, Vistas, Chennai. My topic is molecular orbital structure of benzene, and it is covered under B.Pharmacy third semester under the course Pharmaceutical Organic Chemistry 2 under chapter number 1, benzene and its derivatives. Coming to the contents of my topic, I am going to give a brief introduction about benzene structure and then geometry of benzene based upon sp2 hybridization, and we are going to discuss the unusual stability of benzene based on delocalization of electron cloud, and we are going to summarize with a quiz. So coming to the benzene structure was first discovered by August Kekulé in the year 1865, and he has postulated the structure of benzene as a cyclic planar structure. So his postulation is based upon a snake is eating its own tail. So the benzene structure will be in the cyclic manner, and it will be like a hexagon as it consists of 6 carbons, and all the 6 carbons are located at the 6 corners of hexagon. All the 6 carbons will form a bond with hydrogen, so the molecular formula will be C6H6. August Kekulé has found the 2 Kekulé structures of benzene in which both single and double bonds are arranged at an alternate position. These structures you can see at the right top corner. In these structures, the position of double bond is not at exactly same position. In first structure, the double bond is present between first and second carbon, whereas in second structure, the same double bond will be existing between second and third carbon. So, due to this concept, August Kekulé is unable to explain why the benzene structure is having equal bond length. According to his postulation, he was telling that whenever the double bond is being present in benzene structure, it will be having shorter bond length, and wherever the single bond is there, it will be having longer bond length. So the unequal distribution of bond length will be existing in benzene, but originally it doesn't. All the bonds in benzene is having equal bond length, that is 1.40 angstroms, which is an average of single and double bond length 1.54 and 1.34 angstroms. And he is unable to explain the stability of benzene and also its reactivity. Generally, whenever a compound is having double bonds, it will break and it will undergo electrophilic addition. Surprisingly, benzene is not undergoing electrophilic addition. It wants to stabilize its double bonds, and it is undergoing a reactivity called as electrophilic substitution reactions. So this unusual stability and also reactivity was unable to explain by Kekulé. After a few more years, another scientist from America called as Linus Pauling has suggested that benzene structure doesn't exist in 2 Kekulé forms, but it will equilibrate between the 2 Kekulé structures, and it is called as a resonance hybrid, which you can see at the bottom right corner. One more scientist called as Kathleen Lonsdale in the year 1926, he has told that the benzene structure is flat planar by using his X-ray diffraction studies. The structure of benzene is better understood by molecular orbital theory. In this you can see 2 pictures. The right side picture will signify about the unhybridized p-z orbitals, and whereas the left side picture signifies the presence of sigma bonds in the benzene. To understand all this concept, first you have to know the atomic number of carbon, which is 6. So 6 electrons in carbon is distributed in ground state as 1s2, 2s2, 2px1, 2py1 and 2pz0. In ground state, the 2s orbitals having 2 electrons will be excited, and it will go to 2pz0. So thereby in excited state, the electron configuration will be 1s2, 2s1, 2px1, 2py1 and 2pz1. So totally 4 half-filled orbitals are existing. So carbon is able to form 4 bonds each. That's the reason it is having a valency of 4. So in excited state, as 1s and 3p orbitals are there, among them 1s and 2p orbitals will get hybridized to form 3 equal energy and identical shape sp2 hybridized orbitals, leaving behind 1 pz orbital as such. Each corner of the hexagon represents each carbon, which is going to form the sigma bonds. As three sp2 hybridized orbitals are present, it will form three sigma bonds. With the two adjacent carbons, it will form two CC sigma bonds. Overall, it will likewise, while overlapping, it will form six CC sigma bonds, and one more hybridized orbital which is left over will form a bond with hydrogen to form CH bonds. As six carbons are there, total six CH bonds are going to form, which will produce a plane of sigma bonds called as sigma plane of benzene. To this sigma plane of benzene, the pz orbital will be aligned perpendicular, and the two lobes which are present above and below the plane of these sigma bonds will overlap sideways to form pi bond. Delocalized pi electron cloud. So as you can see in the picture, whatever the pi bonds are present, it will be having two lobes. One is above and one is below the sigma plane, which will overlap sideways, and at once the delocalization of pi electrons will occur. The reason behind this is actually whatever the double bonds are being formed, the carbon has the property to form the double bond on either sides equally. So instead of the double bonds being localized at one position, it is assumed that all the six pi electrons which are shared between all the six carbons, giving a delocalized pi electron cloud. So two orange color rings which you are able to see is due to overlap of the upper lobes and lower lobes of your benzene ring to give upper and lower pi electron cloud. So this is the reason why your benzene is being stable and it is not going to break any of its double bond, and it will give a resonance structure. Based upon this concept, we are able to explain why the benzene is having equal bond length also. So in each side you can see one sigma bond and half of the double bond will be existing. So an average between a sigma bond and a double bond length will be existing in benzene structure, that is 1.40 angstroms. And as the benzene is arranged in a hexagon position, the bond angle will be 120 degrees. Due to this delocalization, the benzene structure is overall more stable and it doesn't undergo electrophilic addition reactions, but instead of that it will undergo electrophilic substitution reactions, preserving these double bonds. Once we are taking the theory concepts, the students will get bored. So it's better to introduce some icebreakers in between so that the students will get regenerated with the concepts of icebreakers. So in between the theory class, you can ask some of the questions like whether you are getting the topic interesting or whether you like the subject, or you can ask some more questions like what was the most challenging subject in your previous semester, or which class do you like you want to implement any animated videos in this class, like that you can ask them. So the students will be a little more interactive, giving their suggestions, and they will get deviate from the little bit from the theory concept, and they will give you more suggestions, and you can implement in the future classes. By asking these questions, the students will be more attracted for your class, and if you take another theory concepts also, they will listen it carefully. At the end of any session, you can conduct a quiz also. So by this, you will understand how much percentage of the students have understood the concepts clearly. So here I have discussed only few questions from the topic whatever I have covered just now. So first question carries arenes do not show. So generally, if you see option number A, arenes means aromatic compounds, it will show delocalization of pi electrons. So option A will be going along with the concept. And whether it shows the greater stability, yes, it shows. It is showing the resonance. Yeah, benzene structure will show the resonance, but whether it will go undergo electrophilic additions, no, it doesn't. So generally, arenes or aromatic compounds, it will undergo electrophilic substitution reactions. So option D will be the correct option. Coming to the second question, which statement about benzene is incorrect? So the carbon ring is planar. Yes, it is correct. The reactivity of benzene reflects the presence of carbon-carbon double bond. Actually, the reactivity signifies it is undergoing substitution reactions but not addition reactions. So it doesn't signifies that carbon-carbon double bond is present in the benzene. So option B will be the correct option because your benzene, based upon reactivity, you can't tell it has any double bonds. Then the C bit, CC pi bonding is delocalized. So definitely it is delocalized, and each carbon is sp2 hybridized. So A, C and D goes with the concept, whereas B doesn't goes with the concept. So your option B will be the correct answer. Then select the correct statement regarding the aromatic carbon molecule. So carbons which are present in aromatic compounds, generally it will be sp2 hybridized. So these things you can collect from the students, and a competitiveness will be increased so that in a better way they will understand the concepts. So these are the references from which I have gathered my information. Thank you. Happy learning.